Hello everyone. Today I am going to design a wireless implantable medical device antenna, which will be 5 millimeter. So I will showing the full tutorial how I make design it. So first of all, make a new template. Here you need to select microwave and RF control antenna. Next, then I am going to design a planar patch type antenna, so I will be choosing the planar time domain. Next, and on the frequency of 0 to 3 gigahertz range, I'm going to get the result of E field, H field and far field. And 2.4 giga, I will put the frequencies 2.4, 2.45. You can put anything, 0.9, 0.915, 0.202. Okay, click next. Okay, so this is the simulation page. I'm going to design in this antenna inside the skin. So let's first of all design skin material. I will select the brick, escape. I will name as a skin. The x minimum would be the 100 by 2 minus 100 by 2 minus, okay, x max, okay, y minimum is also minus 100 by 2, y maximum is 100 by 2 and z maximum is also 100 by 2, and the material would be skin. So let's make the skin material. The epsilon for the skin is 40 and the conductivity is 0.88. Apply. Okay, it's a preview. Okay, so this is our skin material. I am going to design the antenna inside the skin here. So let me fit the local WCS in the middle. Let me align this. 25 would be the middle. Okay, okay, so inside this skin I will make the antenna. I can hide the skin material, so it will be easier to design the antenna, patch antenna. So first of all we need to design the substrate. Okay, I can select the brick and name substrate. Okay, substrate U minimum would be, let's say, W minus W by 2. Copy, paste, minus, and the thickness, the W max is the thickness of the substrate. The thickness would be TS. Thickness would be TS, and material would be the Roger 5880. Let's see, where is the Roger 5880 lossy metal. Okay, load. Now put the value of W, as I am going to design 5 millimeters, so I am going to click 5, and the thickness of the skin is thickness of the substrate is 0.125. Okay, so this is our substrate. You can see. Click OK. Click none. Okay, so I'm going to change the color of the substrate. Let me change to brown. Okay, now let's see, change to blue. Okay, you can select any color, this is not a matter. Okay, now I'm going to design the patch for my antenna. First of all, let me select the surface. I'm going to select on this surface. Okay, now curve. You can design any shape. I'm going to design X-shaped antenna. Okay, let me design. Okay, this is it. Click OK. Select and then enter. I will name this as patch. This is the patch. The thickness would be TP and the material would be the copper. So copper is copper anode on this one. Okay, load, preview. The thickness of the patch would be 0.0175. 0.0175. Okay, click OK, and this is the patch. Click OK. So as the patch, you can transfer, select the patch, click transfer, click rotate and copy. Okay. As I am going to make X-shaped antenna, so copy it to the okay. So now I am going to add these two together. So this is the patch of my antenna, and now I need to design the ground patch. Previously I made the main patch and this is the ground patch. Okay, so as I am going to design the back side, so I need, first of all I need to select the back surface. Okay, okay, my not selected. Things now okay. I have selected the backside surface. Now I'm going to design the patch. Wait a minute, it will be easy. Okay, let me name as ground. Okay, double click on it. This one, enter. This one is ground. Okay, the thickness would be the minus tp, minus tp. Preview. Okay, component material is also copper. Okay, yes. Okay, I am at it. Again select this, transform, rotate and copy, apply. I'll need to make it on the every side. Okay, now I'll connect those together. William. So you can see this is my main page and this is my ground page. So to connect this main page to ground page, or you can say to shorting these two patches, I'll design a shorting pin. So from the ground page it will be easier to connect this. First of all, I can select the local axis on this side. Okay, for the shorting pin, this is, I will select the cylindrical side. Wait, scheme. So cylindrical outer radius would be 0.5 by 2. Let's see. Okay, 0.3 in the middle. Okay, it's good. Material would be copper annealed. Copper. Okay. And Wmax would be minus TP, thickness of the patch, minus TS, thickness of the substrate, and minus TP, thickness of the patch again. I can preview the thickness I made to connect these two patches together, the ground patch and the main patch, so it can be shorted. Click OK. So this is our patch. Let's change the color of the patch. Let's change to okay. Cancel. So this is the solid on this one. Let's rename it as pin 1, and change the color. And so let's change the color as okay. So this is our shorting pin. So let's make another shorting pin. Select pin, transform, copy, and this side, apply. Okay, so this is our two shorting pins to connect the ground patch and the main patch together. Now I am going to design the feet. Again select local axis, let me select there. And now I can select the cylindrical shape. Let's name it as feet. Radius 0.5 by 2, 0.5 by 2. Let's preview. Let's center it. 0.35. Okay, 0.4. 0.4, 0.45. U center 0.15. Okay, now material is also copper. Okay, let's change the feed color. The material is changed to green. Okay, now on this side also I have to make another feed. Again, select here. Okay, okay, cylindrical shape, feed 2, sorry, feed 2, and it is 0.5 by 2 preview, center 4, 7. Okay, 1.5. 1.2. Okay, U center 3. No, it's too much, too 5. Okay, also this is TP. TP. So TP. Need to make the thickness of the patch. Cancel. Feed to define cylinder. I made a mistake, sorry. Delete. Thickness will be TP. I will make the feed thickness to TP. Sorry, minus TP. Minus TP. So I need to make the feed inside the patch, not, it cannot be feed in the substrate or anything. So okay, it is fitted. Okay, I need to transform in this side also. I need to make sure it aligns with the patch, not with the substrate. Okay. Okay, perfect. It one. Transform, copy. Copy. Okay, this is now both the feet is placed on the both side of the patch, not on the substrate. Perfect. Now let me add these two pieces together. Okay, now I need to connect these two pieces with the port point. First select the center to circle this surface, and again pick point on circle. Yes, pick circle center this surface, and go to the simulation, this kit port, impedance is 50 ohms. Okay, apply. Okay, I think need to change the direction of the port. Yes, the port. Yeah, edit, define port, invert direction. I cancel. Okay. Okay, invert direction. Okay, so our antenna is complete. It's pretty easy. Now let me simulate this. First setup solver. Okay, let me check first post processing as parameter. Okay, okay, start the simulation. It will take some time for simulating. We have to wait. Here you can see the progress is simulating. It will take some time. So you can see our antenna is very small, as it is implantable antenna inside the human body. It takes time to simulate. You can see the 3D view of our antenna. So these two red ones are the port which works as a shorting pin for this surface patch, main patch and the ground patch, and these are the feet where we connect the port. And blue one is the our substrate, antenna substrate, which material is Roger 5880 lossy material. And thickness of the substrate, you can see the thickness of the substrate is 0.125, and the thickness of the patch in this yellow one is the 0.0175. So by using this CST Studio 2025 software, you can easily simulate any antennas according to your requirements. It's also almost done, you can see. Why it is taking so time? You can see the countdown here showing 172 seconds, 167 seconds. it is still in progress of simulation. Simulation is almost finished. I can see 99%. So the simulation is finished, successfully finished. Here you can see successfully finished secondary quality evaluation. So our simulation results appears here. 1D results. You can see the port signal as parameter, reference impedance, balance, power, energy, discrete ports, air efficiency. Also we have 2D results. So first of all, let's see the port signal results. You can see here the red ones port signal shows the input and reflected signal. Here red ones are the input signals and blue ones are the reflected signals. If you can see the S parameters, you can see at the 2.4 2 point something 2.1 or frequency has the minus dB S parameter, which is this the S parameter which is actually the reflection coefficient. You can see when the curve goes down, the antenna works better. The deepest dip is around 2.2 gigahertz. At this frequency, most of the power goes into the antenna, which is ideal for medical implements. So then the reference impedance, you can see reference impedance. This graph just shows that the antenna is tested using standard 50 ohm systems, which is normal for RF antennas. It confirms that my simulation setup is correct. We see the balance as parameters, balance, magnitude. You can see this graph shows whether the antenna is excited properly and evenly. The base balance happens near 2.1 gigahertz, where the antenna works best. A balanced antenna works more reliably and stably. And then the power flow, let me select the excitation. Here the red ones are the loss in dielectrics, green and purple one is the green ones is the loss in metals. You can see the loss is very low, and the power radiated no power is radiated. The input signal is observed nicely. The yellowish line is the power outgoing outputs, and the blue one is power accepted. You can see the acceptation rate is very high, and the power outgoing all the power is outgoing all the ports. So this graph shows what happens to the power I send into the antenna. Most power is absorbed by human tissue. Okay, very little power is radiated. Very little, you can see the almost zero, almost no power loss in the metal. Human body tissues absorbs energy, so low radiation is expected for implanted antennas. So now you can see the field energy. This field energy, this graph shows how energy builds up and then disappears. You can see initial, you can see the 0.6 or 7 seconds, nanoseconds. The energy rises quickly, then it smoothly goes down. It means no energy is trapped, which is safer for human body. Okay, next let's see our port connections. Result, current. This is the current, discrete port current magnitude. Current rises frequency, increasing of frequency. Current rises when the signal starts and then it down smoothly. It shows normal antenna behavior with no instability. If you see the impedance, port impedance, this graph shows how the antenna's resistance changes with frequency. Impedance changes with frequency. This value changes because the antenna is inside the human body. Human tissues changes antenna impedance and it's expected. And if we see the voltage, and also the voltage at the antenna input over time, changes in voltage antenna over time, the voltage increases and then smoothly decreases after some times. Again, no sudden spikes, meaning safe electrical operation. There is no sudden spikes, that means it is safe for electrical operations. This is frequency domain. Okay, if we see the lossy material, this graph shows, this graph compares real material behavior with simulated results. Both graphs match very well. Epsilon feet, tangent feet. Okay, and this is the efficiency curve. Red was the, this graph shows how efficient the antenna is. The efficiency is very low. It is not a problem. Implant antennas always have low efficiency because the body absorbs energy. So this efficiency, you can see, is pretty much low. This is the VSWR curve. This graph is another way to show impedance matching. You can see VSWR is high because the antenna is implanted. For implant antennas, the S parameter is more important than VSWR. This is Y matrix, parameters, magnitude with frequency domain. Useful for circuit designers, not critical or antenna performance discussion. See the Z parameters. This graph shows antenna behavior in terms of voltage and resistance. Peak show, this peak show where the antenna resonates. It again confirms the antenna's working frequency. Now if we need to see the electric fields for frequency 2.4, electric field directions. For the 3 gigahertz, it's like that. The H field for 2.4 gigahertz, this is the H field for 2.4 gigahertz, and the surface current for 2.45. You can see the direction of current flowing. ampere per meter in this ampere per meters. The interesting is far field. You can see far field for 2.4 is 3D view of far field for 2.4 frequency, 2.4 gigahertz frequency. For 3 it is like that, and for the minimum I selected is almost rounded spherical type. So this is my antennas design. Okay, thank you.